Hello guys, welcome to Datasets Analytics. In today's session, we will implement Generative Adversarial Networks or GANs. So first set the runtime as GPU. Let's save this and let's connect to T4 GPU. Now, in order to start, first we need to mount Google Drive. So from google.colab, import drive. Then we need to write drive.mount content and then drive. Okay, let's run this code. Let's give the permission to connect to our Google Drive. Select the account and select continue and allow. Okay, so now we have given our code the permission to access Google Drive so that we can access the data which is stored in my Google Drive. Now let's import libraries which are required in this project. So import numpy as np, for now we need these libraries. Let's import them and run this block of code. Okay, so I have done one typo error. Let's hope it works now. Okay, it executed successfully. Now we need to have helper function to display images. So in order to get this helper function, you can visit my Git repository. I'll paste the URL in the description box and you can simply copy this block of code. That's it, and you need to simply run this block of code. So this block of code will be used to display images. Whenever you call this display method, you can display any image. Now the next step is data preparation. So let's prepare the data. So let me give you a brief introduction about this data. We will be first downloading this training data, and this training data is images of bricks dataset which is available on Kaggle. It contains 40,000 computer rendered images of 50 toy brick types captured from various angles or different angles. Now we can go to this block of code, this Kaggle. I'll also paste the URL in the description and you can easily download the entire dataset in your Google Drive. Now you need to add this Kaggle username, this Kaggle key, and then mount this particular drive, your entire drive. Then you need to give the dataset name. So here you can give the dataset name like this, the owner name followed by the dataset name, that is Lego brick images, and then you can simply give it to the destination path where the data will be downloaded, and then simply the data will be downloaded in this content drive downloaded data. That's it. So as these credentials are like confidential, that's why I have written this as XXX. You have to add your own Kaggle username, Kaggle key here, and then the dataset name here. Okay, so I'll post this URL in the description box. Please get this code, first download the entire data and then come back to implementation. As I have already downloaded the entire dataset, the dataset is huge, so we will load sample 100 images, sorry 1000 images. Now this 1000 images will be used for training. We will not be training the entire architecture of generative adversarial networks on millions of dataset, because that will take lots of time, lots of days actually to run on this Google Colab, because the GPU is not that strong. So let's import OS. My source directory is, so this is a directory wherein I downloaded the entire bricks or Lego bricks dataset. My destination directory would be, so this is my destination directory wherein I'll copy sample 1000 images from this source directory to this destination directory. Now let's write a block of code like if destination directory exists, then delete it, right? So I'll write a delete command. Delete command is as follows: rm minus rf, and then I'll give the destination directory, destination directory dir plus, that's it. So as it is, destination directory has spaces, right? This has spaces, so I need to encode this in a double quotes. So I need to write like something like this. Yeah, this will work. And then I'll call os.system so that this command will be executed, del_cmd. Yeah, that's it. And then I'll write a make directory command so that automatically this destination directory will be created at this location. So mkdir command, which will be equal to mkdir minus p. Then I need to encode this into double inverted quotes, and then destination directory plus the similar thing. Then os.system so that this make directory command will run mkdir cmd. Okay. Now let's list down all the files which are available in the source directory. Now let's say we need to copy 1000 images, right? So I have specified n images as 1000 images. Now for index comma img underscore name in tqdm all underscore files. Okay. Then I'll write cp command, that is the copy command. Copy command will be cp space. First I need to have source, right? So os.path.join source directory comma img name, and then encode it in double inverted quotes. Then add a space. Then I need to verify. Then we need to add the destination directory or destination directory. path.join destination directory with same image name, and then let's encode it in double inverted quotes, and then let's execute this command cmd. Okay. Now we need to write a logic so that after copying 1000 images, this loop stops executing. So if index is greater than, so this index, if this index is greater than n images, number of images, then we need to break or come out of this particular loop. So let's run this block of code. So we have encountered one error, that is too many values to unpack. It is because we have just used TQDM, we have not used enumerate. So we will write here enumerate and then run this particular block of code. So now you can see that each one of the images is copying. The speed is not that good, but still it is copying. Now let's wait couple of minutes and let's get back after entire thing is copied. All the 1000 images are copied and it took about 6 minutes 50 seconds, approximately 7 minutes to copy, because it is a Google Drive. The copying operations happening is slow. Now we will use this Keras image dataset from dictionary. Now we need to convert these images into a TensorFlow dataset. So now we will use Keras function, which is called as image dataset from directory, to create a TensorFlow dataset. Let's take a variable. Let's take train data, which equals to utils dot image dataset from directory. So basically it will convert this images folder to TensorFlow dataset, which is pointed directly where the input images are stored. So the first will be the folder in which our images reside. So destination folder. Okay, destination dir we have, destination dir. Then we have labels as none. Then color mode. Color mode let's keep as grayscale. Then let's specify image size. Image size will be equal to 64, 64. So this is nothing but the image resolution or resolution of image. Then batch size, let's keep batch size as 128. Then shuffle will be true. Let's take a seed point as 42. You can take any random number as seed point. This seed we are using so that the results are repeatable. Then interpolation as bilinear. That's it. Let's run this block of code. So it found 1002 images belonging to only one classes. That's it. So this train data is now a TensorFlow dataset. So let's print the type of train data. So this is TensorFlow, Python, data ops, prefetch op, and so on. So this is now a TensorFlow dataset. Now this lets us load images batches on the fly as needed, that is during training. Now enabling us to handle large datasets without the need to store entire dataset in memory. Additionally, it resizes the images to 64 x 64, smoothing pixel values in between. So this is the advantage of loading images like this. Now let's pre-process the data, right? So let's do the data pre-processing. Now the initial data has pixel intensities within the range 0 to 255. Now when training the generative adversarial networks, we adjust the scale to -1 to 1. Now this adjustment allows us to use tan hyperbolic activation function in generator's final layer, which tends to offer more robust and stronger gradients when we compare it to sigmoid function, and that's why we are doing this data pre-processing. Let's write a function, a simple function to pre-process this data. Okay, now it will do the functionality of normalizing and reshaping the images. So this img will be equal to tf dot cast img comma float 32 minus 127.5 divided by 127.5, and then I will simply return img. Okay, now that we have built function, let's call this function. So train equal to train underscore data. We will use the functionality of map. Then we will use this lambda function, lambda lambda x. Then preprocess, we will call this function process preprocess x. Okay, lambda it will be. Okay, then let's run this. That's it. The images are now preprocessed. The preprocessed images will be now in the range of -1 to 1, and I have already explained why it has to be in -1. Let's take sample amount of data and let's try to visualize few images. So we will use this sample batch. Now this sample batch is from this helper function which we copied it from the GitHub repository. So this is the sample batch. Okay, sample batch from train, and let's display few images from train sample. That's it. So these are the images in our training data. So these are the Lego bricks dataset. Now let's come to the most important part, that is to design the discriminator. Now let's design the discriminator part. Now here the task of this discriminator is to determine whether an image is a real or fake image, essentially making it as a supervised image classification problem. So we can use similar architecture to what we discussed in the autoencoder session with just one output node. So let's define the discriminator here, or let's define the input to the discriminator. So discriminator input would be equal to layers dot input. Here we will give shape equal to 64 cross 64 comma 64 comma 1. Then we need to stack convolutional 2D layers on top of each other with batch normalization, and we will be adding leaky ReLU and dropout layers which is sandwiched between them. So first we will stack conv 2D layer with obviously batch normalization. So let's stack these layers. So the first convolutional 2D layer is as follows: x equals to layers dot con 2D. The feature size will be 64, kernel size will be equal to 4, and strides will be equal to 2. Padding we will keep it as same, and we will not use bias, so use bias will be equal to false. Now the input to this will be the discriminator output, discriminator input. So I'll just copy paste this one. Okay, now we will type x equal to layers dot leaky ReLU, leaky ReLU, that is the activation function. We will give here 0.2, and then input would be x. Now we need to add dropout, so x will be equal to layers dot dropout. The dropout probability we will keep at 0.3. Input will be x. So this is the first convolutional neural network. This is the first convolutional 2D layer. Now let's write the next con 2D layer. So I'll just copy paste this particular syntax from here, and then we'll put here instead of 64, now we will have 128, and instead of discriminator input we will have X. Now we will write this like we will now add batch normalization. So layers dot batch normalization with momentum equal to 0.9, and input would be X. Now we will add leaky RELU with the same thing as we have written here, and we will add dropout as well. This is the second convolutional layer. Okay, this is 2D. Now this is also 2D, 2 and then D, capital D. Okay, now two convolutional layers are done. Now we will write the third convolutional layer, and for writing this third convolutional layer I will simply copy this and paste it here. Instead of 128, now I will write 256, and strides will be equal to 2, kernel size will be 4, padding will be same, use bias will be equal to false, input will be X, and the rest remains similar. Now let's add next convolutional 2D layer. Now instead of 256 we will write here 512, and other things will be same. Okay, now that's it with convolutional layer. Now what we will do is we will flatten the last convolutional layer. So by this point the shape of the tensor is 1 cross 1 cross 1, so there is no need for final dense layer. So X equal to layers dot con 2D, the size will be 1, kernel size will be equal to 4, strides will be equal to 1, padding will be equal to valid, use bias will be equal to false, and activation will be equal to sigmoid. That's it, and input will be X. Okay, now we will have another variable, that is discriminator output. This discriminator output will be layers dot flatten and X, input will be X. Now we will type here Keras model, that is discriminator equal to models dot model. Now this defines the entire discriminator. Now this discriminator is nothing but a model that takes an input image and outputs a single number between 0 and 1. Here we will give discriminator input and discriminator output. Okay, and then we will just print the summary of this discriminator dot summary. Now let's run this particular block of code. Here we can see the entire parameters and everything about the discriminator. So now let's design the generator. This generator takes a vector sampled from multivariate standard normal distribution as input and produces image of the same size as those in the original training data. Now this generator role might sound similar to the decoder in variational autoencoder, right? So if you haven't watched variational autoencoder session which I have uploaded, I'll post the link in the description. In fact, the GANs generator serves the same purpose as variational autoencoder's decoder, which is to transform a latent space vector into an image. This idea of mapping from latent space back to the original domain is widely used in generative AI or generative modeling. It allows us to manipulate the latent space to alter high-level features of images in the original domain. So let's start coding the generator part. Now let's define input to the generator, which is a vector of length 100. So generator input will be layers dot input shape equal to 100. Now we will use reshape layers to give 1 cross 1 cross 100 tensor, so that we can start applying convolutional transpose operations. So layers dot reshape 1 cross 1 cross 100, and then the input will be generator input. Now we are doing this because we can start applying convolutional transpose operations. Okay, now we will pass this through 4 convolutional 2D transpose layers with batch normalization and leaky ReLU layers, which is sandwiched between them, as we have done in the discriminator. So X will be layers dot con 2D transpose comma kernel size will be 4, strides will be equal to 1, padding will be equal to valid, use bias will be equal to false, and input will be X. That's it. And now we need to apply batch normalization. Layers dot batch normalization, momentum will be equal to 0.9, input will be X. Again we will have to apply this layers dot leaky ReLU activation function, and then input will be X. Now let's define second convolutional layer. I'll just copy this, paste it here, and we will have to instead of 512 we now need 256, and we'll use padding as same, and again there will be batch normalization and leaky ReLU activation function. That's it. Now we will define third convolutional layer, wherein this will be 128, kernel size will be 4, strides will be equal to 2, strides it has to be 2, right? And here the strides again has to be 2 because we are downsampling now. Padding use bias will be equal to X, then batch normalization will be same, leaky ReLU will be same. That's it. This is the third convolutional layer. Now final convolutional layer we will write. This will be generator output. Generator output will be layers dot conv 2D transpose 1 comma kernel size will be 4, strides will be 2, padding we will keep as same, then use bias will be equal to false, and activation will be equal to tan hyperbolic. This is important, and input will be X. Now we will define the final Keras model. So generator will be equal to models.model generator input. I'll simply copy paste. First it will be input as we have done during discriminator. So it will be input and then output. Now this Keras model defines the generator, that is a model which accepts vector of length 100 and outputs a tensor of shape 60. Now this Keras model, it defines the generator. That is a model that accepts a vector of length 100 and outputs a tensor of shape 64, 64, 1. And let's print the summary. Generator.summary. Let's run this. Okay, we have got one error, that is kernel size in 17th line of in 17th line. 17th. Okay. Oh, kernel. It should be kernel. That's it. So this is the entire architecture of the generator, and we can see here the total trainable parameters are this. Total parameters are this, trainable are this, and non-trainables are this. So I have done one mistake here. After analyzing this particular architecture, I have just realized that I have missed one convolution layer. So in this generator we have this 64, 128, 256 and final one, right? But here we don't have the 64th this one. So what we will write here, I'll just copy paste it here, and then we have to make it 64 here. I think everything else will be same. Let's run this. Now I'll again analyze this particular architecture. There is one mistake which I have done in the generator output. The kernel size has to be 4, else there will be a dimension mismatch. Let's again run this. Now it is good. Now the architecture is good. Now here we can observe that we have applied a stride of 2 in this convolutional layers or convolutional transpose layers to increase the tensor size through the network, that is from 1 to 4, 4 to 8, 8 to 16, 16 to 32 and finally to 64, and that's why we needed to add this particular layer which we missed, while reducing the number of channels, that is the channels were 512, 256, 128 and 64, and ultimately the channel was 1 to match the grayscale output. So in this way we have successfully designed the generator part. So now that we have designed both the generator and the discriminator modules, let's start with the actual training script. So let's train our DCGAN, that is Deep Convolutional Generative Adversarial Networks. Now the Keras library provides us with the ability to create a custom train step function to implement the logic for training. So we will add here class DCGAN and here we will give models.model. Then we will have init functionality. This init will have self, then it will have discriminator, then we have generator, then we have latent dimensions, our dimensionality. Then we will use the super keyword DCGAN, self dot init. Okay, now this self dot with the discriminator will be equal to discriminator, and then self dot generator will be equal to generator, and self dot latent dimensions will be equal to latent dimensions. Okay, now we will write a function to compile. So def compile self dot optimizer G and D stands for discriminator and generator respectively. Then we will again use the super keyword DCGAN, self dot compile. Okay, now we will be using binary cross entropy, this both for generator and discriminator, right? So we will have self dot loss function equal to losses dot binary cross entropy. So this will be the loss which will be used for both generator and discriminator. Now we will write self dot d optimizer, that is discriminator optimizer, equal to d optimizer, and self dot g optimizer, that is generator optimizer, will be equal to generator optimizer. Then we will have self dot discriminator loss metric. Okay, we will have metrics dot mean, we will give name as discriminator loss. Similarly, we will have self dot this one real discriminator real accuracy metric, which will be equal to metrics dot binary accuracy. Here name will be equal to d underscore real accuracy, the real images accuracy for real images. Now we will have fake self dot d underscore fake accuracy metric, which will be equal to matrix dot binary accuracy, name will be equal to d fake accuracy. Then we will have accuracy metric, so self dot DACC metric equal to matrix dot binary binary accuracy name equal to discriminator accuracy. So now we will have generator loss metric, so self dot generator loss metric, which will be equal to matrix dot mean and name equal to generator loss. Similarly, self dot generator accuracy metric will be equal to matrix dot binary accuracy, name will be generator accuracy. That's it. Now we will define all these metrics to return. So we will have this property decorator, and we will write a function, that is def matrix self, and then we will write here return. First we will have self dot d loss metric, then a real accuracy metric, then self dot fake accuracy metric for fake images, then overall accuracy, that is self dot this one accuracy metric, and then for discriminator we will have this, for generator we will have this, and self dot final accuracy metric. That's it. Okay, now this compile functionality and metrics functionality is done. Now let's try the actual code where training will happen, that is the train step. So def train step, here first it will be self, then the input will be real images, not real images, real images. Okay, now we will sample random points in the latent space. So to sample that, we need to have batch size, which will be equal to tf dot shape real images of 0. Then to train the neural network, to train this entire network, first take a sample batch of vectors from multivariate standard normal distribution. So random latent vectors equals to tf dot random dot normal. In that we will add here shape will be equal to batch size and then self dot latent dimensions. Now let's train the discriminator on fake images. So with tf dot gradient tape. So in the previous session, while implementing autoencoders, I have already explained why we use gradient tape, so I will not repeat it once again. If you want, you can refer that particular video as gen tape comma tf dot gradient tape as disk tape. Enter. Now we will pass this batch of vectors through the generator to produce a batch of generated images. So generated images will be equal to self dot generator, then random latent vectors, and then training would be equal to true. So that's it. So we have passed this random latent vector to the generator. Now we will ask a discriminator to predict whether the generated images are real or not. So we will call the discriminator here. So with this random noise, generator generated some images, and now we are calling discriminator to predict whether the generated images are real or not. So real predictions equal to self dot discriminator real images comma training will be equal to true. This will check, or this will predict the realness of the batch of real images, and also we have to check for fake images, right? So fake predictions equal to self dot discriminator. In this we will pass generated images, and similarly training will be equal to true. Right, that's it. Now one trick we will add a noise to the labels. Okay, now this is one of the helpful technique in GAN training. It involves adding slight noise in the labels, a random noise. Now this boosts training stability and enhances the image quality. Now label smoothing acts as a way to tame the discriminator so that it is presented with a more challenging task and does not overpower the generator. So here the idea of adding noise is the discriminator should not overpower the generator. So we will add a random noise. So real labels equal to, and we will add noise to the labels so that the discriminator won't overpower the generator. So real labels equal to tf dot ones real predictions, then real noisy labels will be equal to real labels plus, now we will add the noise, 0.1 into tf dot random dot uniform, and in this we will give tf dot shape. The shape is of real images, real predictions. Okay, similarly, we will have fake labels. Fake labels will be tf dot zeros, right? So zeros like, uh, here also tf dot ones like, tf dot zeros like, fake predictions, and fake noisy labels will be equal to tf dot same sorry fake labels into 0.1. So here we have added, right, and here we will use subtraction. 0.1 into tf dot random dot uniform, then we will add tf dot shape and fake predictions. That's it. We have successfully added noise to the label so that discriminator won't overpower the generator. Now the discriminator loss is average binary cross entropy loss with both the real images and the fake images, because it is a classification problem. So we will now add losses. So d underscore real images loss equal to self dot loss loss functionality. Here we will add here real noisy labels comma real predictions. Similarly, we will have this loss, fake loss. Discriminators fake loss will be equal to self dot loss functionality fake noisy labels and fake predictions, and then discriminator, finally the discriminator loss. So here the loss will be real loss comma plus a fake loss divided by 2. Okay, now the generator loss is binary cross entropy between discriminator predictions for the generated image and the label of 1. So we will write generator loss is self dot loss functionality. It is between real labels and fake predictions. Now let's come out of this particular loop. The loop was this one with tf dot gradient tape. Now let's update the weights of discriminator and generator separately. So in order to update that, we will have to write couple of lines. So gradients of discriminator will be equal to disc underscore tape dot gradient the loss of the discriminator and self dot discriminator dot trainable this variables. Now we will write gradients for gradients of generator, which will be gen underscore tape dot gradient. Inside we will have generator loss and self dot generator dot trainable variables. That's it. Now we have this gradients of generator and discriminator, right? Now we will use this apply gradients functionality. So self dot discriminator optimizer dot apply gradients. we have to apply gradients on zip of gradients. I'll just copy paste it so that spelling mistake won't happen, comma, discriminator trainable variables. Okay, now we will have self dot generator optimizer dot apply gradients. Inside zip we will write gradients of generator, and then we will have generator dot trainable variables. Here we will have self. Okay, we don't require self here. Okay. Okay, so now let's update the metrics. Let's update the metrics. So self dot discriminator loss. This is metric, right? Metric dot update state. We will use here discriminator loss. Then self dot discriminator real accuracy metric dot update state. We will have here real labels and real predictions. Then we will update for fake accuracy metric dot update state. This will be fake labels and fake predictions. I'll just make this self spelling correct, SELF. Now we will have self dot what we will have now, this accuracy metric dot update stats. We will write here real labels, fake labels, then real predictions and fake predictions. Now we will have self dot generator loss generator loss metric dot update state generator loss. Then we will have self dot generator loss metric dot update state. Inside this we will have real labels and fake predictions. I think we are good to go now. Okay, so here I think there is some issue with indentation. Let's solve this. Okay. I think this will do. Yeah, this is under. Okay, now it is right. So all these real predictions and all has to be in with this particular loop, and then we are good to go. Yeah, self. Okay, now let's return. So return m dot name, then m return this particular dictionary result for m in this self dot metrics. Let's run this block of code. Now the discriminator and generator are constantly fighting for dominance, right? Which can cause instability in DCGAN training or generative adversarial networks training. Ideally, the training process will find an equilibrium that allows generator to learn meaningful information from the discriminator, and quality of the images will start to improve. After sufficient epochs, the discriminator often becomes more dominant. But this might not matter since, but by that time, the discriminator could have already learned to create good quality images. So let's create a DCGAN. So DCGAN or Deep Convolutional Neural Networks GAN is DCGAN. Here we will write discriminator. Then we will have generator. Then we will have the dimensionality, latent dimensions. Latent dimensions will be equal to, let's keep 100. Let's run this block of code. Okay, this is not defined. I have made a spelling mistake here. We have got one error, that is super keyword has no attribute DCGAN in it. Let's solve this particular error. Here we need to add double underscores or dunder. Yeah, I think we are good to go. Let's rerun this block of code. Okay, again one error on line number 5. Okay, this spelling mistake. Oh, again I have made spelling mistake. SELF. Yeah, now this is executed successfully. Now let's start the actual training, right? Here I'll add, let's start the actual training. In order to start the actual training, we will compile the DCGAN. So DCGAN dot compile D optimizer equal to optimizers dot addm. So we will use here addm optimizer. We will keep here learning rate to be, let's say, 0.002, and let's set the beta to be the beta 1 to be 0.5 and beta 2 to be 0.999. Then we will have the generator optimizer, again optimizers dot addm. Here we will keep the same parameters. I'll just copy paste it here. Okay, let's run this block of code. Optimizers is not defined. Oh, okay. Again a spelling mistake. Let's solve this and rerun this block of code. DCGAN compile got an unexpected keyword argument D optimizer. Let's solve this error. So here I have written D optimizer. So here I will just rename him optimizer, and let's run everything. Again it is saying the same error. Here optimizer, and here also optimizer. Okay, let's run this 3 block of code. Now the errors are gone. Okay, now let's create a model and save the checkpoint. Now let's create a model save checkpoint. So model checkpoint callback equal to callbacks dot model checkpoint. In this we will have to give the file path where the model checkpoint is to be stored, trained model checkpoint. So we will create a folder. The code will automatically create a folder. We just have to write here checkpoint.ckpt. Then there is an option to save weights. So save weights only equal to true. And then we will have save frequency, which will be equal to epoch. And then we will set verbose as 0. Let's now that we have defined this model checkpoint callback, we will have to define TensorBoard callback as well. So TensorBoard callback is equal to callbacks. So it will be beneficial, or it will be useful to display the graphs of how the model is behaving in runtime, like in while training. We can view this one. So we can view the loss behavior as well as the metrics. Now let's define class image generator. We will have callbacks dot callback. Then we will define init functionality, number of image, and latent dimensions. Then self dot number of image will be equal to number of image. Similar with respect to latent dimensions. Equal to latent dimensions. Then we will define function, that is on epoch end, self epoch, and then logs will be equal to none. We will have this random latent vectors equal to tf dot random dot normal. Then we will define shape equal to self dot number of image, and then self dot latent dimensions. Now we will have this generated images section. Generated images, which will be equal to self dot model dot generator. Then we will have random latent vectors. Then we will transform the generated images as follows. So generated images into 127.5 plus 127.5. Now this generated images will be equal to generated images. We will convert it to numpy array dot numpy. That's it. Let's run this block of code. Now let's do the actual fitting of the model. So DCGAN dot fit. Initially we will have to give the training data, which is stored in the train variable. Then we have to give number of epochs. Let's say we want to train for 500 epochs for now. Then we will have callbacks. In this callbacks we will have a list. So first is model checkpoint callback. Then we have TensorBoard callback. Then we have this image generator, wherein we will have number of image equal to 10 and latent dimensions will be equal to 100. Let's run this block of code, and hopefully if there is no error, then the training will start. But we have got one error, that is module TensorFlow has no attribute gradient tape. Okay, so this is one this typographical error. Let's see. Here. So I'll rerun this block of code and let's run this again. We have got another error. Okay, same error. Oh, from where it is coming now? Let's check this error. So here we have written gradient tape and gradient tape. Let's run this. I think it is done. Let's compile this. Okay, we haven't compiled. Now let's run the entire thing. Now the model is like training. Okay, one another error. Attribute binary accuracy has no attribute update stats. Okay, yeah, it won't have update stats, it will have update state. Again, one typographical error. Let's search this and solve this. Here I'll write update state and run the entire block of code. So now as we can see here that the model training is completed and the model is stored. So I have written one line here, that is generator dot save, to save the generator and to save the discriminator. Now you can refer to this code to generate new images. So it is a simple block of code that you can get it from my GitHub repository, and you can see here that the images generated are as follows. So with only by only training this entire model with 1000 images, we are getting this kind of output. Now you can try at your home by taking the entire dataset and on training this particular architecture, model architecture, on entire dataset, and also you can increase the number of epochs as well. So hope you guys learned something new in this particular chapter. So if you have found this video helpful, do like this video, share it with your data enthusiast friends, and bye everyone, take care.